In this video, we're talking about lesson 7-6, growth and decay. There are two parts to this lesson. This first video is all about growth. So we have exponential growth, and we have a formula to represent that. It's exponential because the variable is the exponent. That's what changes. So while the whole formula stays the same, no matter what we put in for our variables, one of the variables is in the exponent, which makes this exponential growth. Okay, so in this formula, y equals a times 1 plus r to the t power, right? So y represents the final amount that we're looking for. A represents the initial amount we start with. R represents the rate of change, and a rate of change is usually like a percentage or a ratio, so we do have to put it in decimal form when we put it in our formula. And t represents time, the amount of time that's passed, okay? So first example here, we have population. The population of Johnson City in 2005 was 25,000. I'm going to highlight some important things here. Anytime you see a number in math, you know that's probably going to be important. Since then, the population has grown at a rate of 3.2% each year. Write an equation to represent the population of Johnson City since 2005. So we want to identify what we know out of y, a, r, and t, okay? Y is the new amount that we're looking for. It doesn't tell us what amount we're looking for after a certain amount of time. It doesn't say, if this is the situation, what was the population in 2012? It doesn't give us a final amount. So we're not going to know y here. We are going to be able to put in numbers for A, R, and T. So A is the initial amount, and our initial amount is 25,000, and that was in the year 2005. Since then, the population has grown at a rate of 3.2%. Now, I know that that is a decimal, but it's a percentage. So even though there's a decimal in the percentage, that doesn't mean we're using 3.2. Whatever a percent is, to change it to a decimal, you're dividing it by 100. So this change to a decimal is going to be 0.032. Okay, so this is R, and this number up here is A. So what they don't tell us here is a year, a time that has passed. It's just kind of in general, so we're going to keep T. And since we don't know what T is, we don't know what y is. We can't solve at the end, right? But we are going to fill in these two things. All right, so we've got A, that's our initial amount we started with. The starting year is 2005. The population was 25,000. So in for A, we put 25,000. I'll highlight that. Boom, boom. We just substituted. And then the rate of change is 3.2%, which is 0.032 in decimal form. So we plugged in place of R, we plug that rate. It doesn't give us an amount of time to go by, so we leave time as t. And since we don't know t, we can't solve the whole thing for an ending amount. All right, so here's our equation. And then once you simplify what's inside parentheses, 1 plus 0.032 is 1.032, then you're done. Okay, the next step here out of order of operations would be to raise this base to the exponent. We don't know what the exponent is, right? You can't multiply these two together until you simplify this term by raising it to the exponent. We can't do that, so we're all done simplifying. So this is our final formula. So now if they followed up with that and they said, what's the population in another year, then you can plug in the amount of time that's passed, and then you can solve the whole thing and figure out what the population is, which is what they do right here. Let me zoom in a little bit. So we've got our formula, and here it says, according to that formula, to that equation, what will the population be in 2015? Well, since our first year was 2005, and 2015 is 10 years later, the amount of time that has passed is 10 units, 10 years. So T is going to be 10. Our ending amount minus our starting, not amount, but our ending year minus our starting year is a difference of 10. So we're going to put 10 in for T, and then we can simplify. So when you raise 1.032 to the 10th power, 1.032. Okay, sorry, I had to check out my calculator. I was today years old when I figured out how to do exponents on this calculator. That's hilarious. All right, so for here, we're trying to simplify this. First thing we want to do is raise 1.032 to the 10th power. Okay, so how do I do that? I'm going to type in my base, 1.032. I'm going to hit this little y to the x button. In this button here, y is your base and x is your exponent. So you type in your base first, hit this, and then type your exponent and hit equals. And that's our answer, 1.37024, blah, 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 blah. And then I want to multiply that by 25,000. So I'm going to hit times 25, 1, 2, 3, boom. 34256, 34256. So our population in 2015 is 34256. That's what we just got on our calculator. Okay, hopefully that's making sense. Let's do one on our own. There's another example up in this guy. It explains to you how to plug stuff in. Oh, we definitely want to do that. Okay, we'll go up there in a second. Let's do this example. Number one, population. The population of the United States has been increasing at an average rate of 0.91%. So that's R. So 0.91% is really 0.0091. If the population was 303,146,000 in 2008, predict the population in 2012. So this was our initial amount. This is A. And then T, the time, 2012 minus 2008, that's 4 years that's gone by since the initial starting point. So T equals 4. So we're going to set up our equation, simplify it, and solve it. So we have y equals A times 1 plus R. A is 303,146,000. 1 plus R, 1 plus R. Remember, this isn't just a decimal, it's a percentage. So you have to still divide it by 100 to put it in decimal. So 0.0091 raised to the 4th power. So when we simplify this, this is going to become 1.0091. 1.0091 raised to the 4th power, and now we can actually solve it. So my calculator, I'm going to put 1.0091, raise it to the 4th power. So 1.0091, hit this little y to the x key here, to the 4th power, equals that long guy, and then I have to multiply that by this long 303,146,000. So times 303,146,000 equals 314,332,051. 314,332,051. 314,332,051. So our initial population is here. It's growing just under 1% per year. So after 4 years of growing almost 1% each year, we get to 314,332,051. Hopefully that makes sense. Number 3, population. Yeah, I think the other two go with that side. It's estimated that the population of the world is increasing at an average annual rate of 1.3%. So there's R. If the 2008 population was this much, so that's our starting amount, our initial amount, predict the 2015 population. So if the starting population was in 2008, 2015 is 7 years later. 2015 minus 2008 is 7. So when I write my equation, I'm going to write y equals the initial amount, it's a long number to write, 641,000,000 plus my rate divided by 100. I have to change percent to a decimal. So 0.013 raised to the 7th power. And of course, when I simplify that, y equals this really long number times 1.013 to the 7th. And now I can simplify that in my calculator. 1.013 raised to the 7th. This little y to the x key, 7 equals that long number. And then I'm going to multiply that by 6641. 000 equals 726,941,7259. Wow. 726,941,7. 726,941,7. 259. 259. Boom, boom, boom. So 7 billion, 269,417,259, okay? On the other side here, we're taking that same formula, going up here to the top where they give you an example, they show you how to solve it, but we're tweaking it a little bit. Okay, so this is an investment. The Garcias have $12,000 in a savings account, so that's their initial amount. Okay. The bank pays 3.5% interest on savings account, compounded monthly. Wait, what? Compounded monthly. What the heck does that mean? Well, we've been talking about an annual rate of change, right? How much it changes in percentage per year. But now it's not changing per year, it's changing per month. So find the balance in 3 years. So 3 is t. Let me use red. T equals 3. Here's our rate. R equals 0.035. You don't see that? Yeah. But then what the heck does compounded monthly? How do I account for that, right? The rate, 3.5, can be written as this. We did that. The special equation for compound interest, we add this little in our equation. So remember before, it was y equals a times 1 plus r raised to the t power, okay? These two letters are still the same thing. It's our ending amount equals our initial amount. But when you're talking about compound interest in money stuff, it's your principal. The principal is the amount of money you start with. So instead of calling it lowercase a for initial amount, now we're calling it uppercase P for principal, but it's the same thing. It's the amount you start with. So total amount equals the amount you start with times 1 plus, so far everything's the same as when we did the exponential growth. Instead of just R, your annual rate, we're going to divide R by N. What is N? N, where does it tell us? N represents the number of times the interest is compounded each year. N represents the number of times the interest is compounded, just meaning how many times it increases each year. It doesn't just increase one time. It increases, it told us monthly. How many months are in a year? 12. So how many times does it increase each year? 12 times, right? So here in our problem, N is going to equal 12. So instead of doing 1 plus r raised to the t power, we're doing 1 plus r divided by the number of times it's compounded, raised to the number of times it's compounded per year, times the number of years, right? Makes sense, right? I know your head's probably spinning and you're like, why are there so many letters? Why are letters in math? It's supposed to be numbers. I get it. It's weird. This looks super hard, right? But it's not. We're not doing anything weird. We're literally taking this and replacing letters with numbers. You just got to know which number goes where. That's all we're doing. And the more you do it, the easier it feels. So once you get comfortable using just this basic formula right here, all we did to this formula was divide r by n and then multiply t times n. That's the only thing that changed from this formula we started with to this really complicated looking one here. I don't know why they changed the name of the variables because they still represent y in lowercase a. All right, so let's plug everything in. So here is our formula. So the amount we're looking for equals the initial amount, 12,000, times 1 plus the annual rate of change, or the rate of change, compounded monthly, divided by 12, because it has to be divided by the number of times per year that it's compounded. Compounded just means like calculated. The number of times per year that they actually increase, that they calculate the increase. And then all that raised to the t, and then you still got to multiply it by n again. So the only thing that changes here is this little extra n step, right? And then once we simplify, just use order of operations, right? We know 3 times 12 is 36. 0.35 divided by 12. 0.035 divided by 12 equals 0.00291, blah, 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 blah. So we know that's equal to 0.0029, blah, blah, blah. Probably in my calculator, it's something where I'll calculate that, and then I won't clear it out. I'll leave that long decimal. I'll add 1. Then I'll raise it to the 36th power. And then whatever all that is, I'll multiply it by 12, right? So we should get this. So let's do that. All right, so I got this, which is this right here. Got this long decimal. Then I want to add 1 plus 1. Then I want to raise it to the 36th power, right? Is it 36? Yeah, 3 times 12. So I'm going to hit, this is my base. I'm going to hit this little y to the x key, and then my exponent equals. Okay, 1.1105, blah, 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 blah. And then I have to take that and multiply it by 12,000. So I'm just going to hit times 12, 1, 2, 3. And I get 13,326.49. 13,326.49, literally the same thing. And it's in money terms, so you can use the first 2 here, right? Because it's money, it's like change. So in 3 years, when they compound the interest every month, so they keep increasing it by that rate of change every month, after 3 years, or 36 times that they're taking that raise, the balancing the account will be $13,326.49. Okay, I hope that makes sense. It really makes life easier if you don't try and clear stuff out on your calculator. Don't estimate and go, okay, well, this is 3. I'll just write that decimal down. I won't put all this stuff in. And then the next step, don't do that. Leave it all in your calculator, okay? I still want to see where you simplify your formula. Once you get your formula simplified, then you can put it all in your calculator. All right, so let's do a couple of these. And you know that it's a compound interest when you see the word compounded, right? So here, I'll highlight it. Or you see stuff about investments, because compound interest is with money. So compounded monthly, compounded quarterly. So we know we're going to be using our compound interest formula, which is the amount we're looking for equals the starting amount, the principal, times 1 plus r raised to the t power, but it's not compounded annually, it's compounded more often than that. So we're going to divide r by the number of times it's compounded per year, and then we're going to multiply t by that same number. Okay, so here we go. Determine the value of an investment of $25,000. That's our principal amount. So A equals 25,000. Oh, sorry, 2,500. Sorry. That's what I get. 2,500. If it's invested at an interest rate of 5.25%, so that's times 1 plus, remember we have to change this to a decimal. It's percentage right now. So I divide by 100. This moves backwards 2 spaces. 0.0525 divided by compounded monthly. That means in a year, we're taking this interest 12 times. So I put a 12 here. For 4 years. So t is 4, and then I got to multiply it by that 12 again. So now I'm going to simplify my formula, and then I'm going to calculate it on my calculator and put it over here. A equals 2,500 times, and then I'm going to go ahead and try and write it. You know what, I'm not, because I want you to put it in your calculator like this. So I'm not even going to simplify this, because I'll have to estimate or round. I'm just going to leave it just like that. And then 4 times 12 is 48. Okay, so let's calculate that. So in my calculator, I'm going to start with changing all this. So 0.0525 divided by 12 plus 1. And then I have to raise it to the 48th power, so I hit this little button. This is my base. Raise to the 48th power equals. So all of this equals this, and then I gotta multiply it, by 2,500 times 2,500 equals 3082.78. 3082.78 equals 3082. All right, makes sense. After 4 years, when we're compounding interest every single month, that happens a lot, right? By the end of 4 years, we're going up from 2,500 to over 3,000. Sounds good. Let's do one more. Investment. Determine the value of an investment of $100,000 if it's invested at an interest rate of 5.2%, compounded quarterly for 12 years. What does compounded quarterly mean? How many quarters are in a whole? 4, right? Like 4 quarters in a dollar. So if you compound something quarterly, it means you do it 4 times a year, right? Like every 3 months. So here, N is going to equal 4. So now we can write this. So the amount we're looking for equals the starting amount, the principal, at an interest rate of times 1 plus, the interest rate is 5.2%. We divide that by 100. So 0.052 all over N. N is 4. Here, I'll do it in a different color. Raised to the t power. It says after 12 years. And then I have to multiply that 12 years times 4. Because it's not just, we're not just compounding the interest for 12 years. We're compounding the interest times how many times each year we compound it, right? Times 12 years. So 4 times 12. We're compounding the interest 48 times. That's a lot. Okay, so now we're going to simplify. 12 times 4, I'm going to go ahead and change that to 48. So there's my formula in my calculator. I hope me doing it is helping you. I hope it's not being annoying. I'm going to do 0.052 divided by 4 plus 1. Raised to the 48th power, hit this button, 48 equals, great, and then I have to multiply it by that initial 100,000. So I'm going to get 185888.87. 185888. 185888.87. And there we go. I mean, that makes sense. After 12 years, when you're compounding the interest, when you're increasing the interest 4 times a year after 12 years, that's a long time, right? You're almost doubling your money. You started with 100,000, you're almost up to 200,000. I mean, not like super close, but you're getting there, right? So that's pretty good. That's the amount you'll end up with. Let me know if you have questions.